How much is Vout over Vin when the op-amps are ideal and are connected like this? We have a common terminal that connects to the two input terminals of the op-amps, and we have also the other terminal connected to the ground like this. The output is tied between the two outputs of the two terminals. So we have to find the VB in relation to VC. Well, first of all, I'm going to say that this circuit does work separately from this circuit over here. I'll name this point X, and I'm going to say that there's a current flowing from here all the way to here. It cannot really flow inside the input of the op-amp, so it has to flow from the ground all the way to this point, and from this point all the way to here. Now, working on this circuit, I can say that V0 minus Vx over 10, the current flowing like this, must be equal to the current flowing like this, Vx minus VB over 20. Alright, this is the resistance in kilo ohms. Now, how much is Vx? Well, Vx is the same as the voltage over here. How much is this voltage? The voltage is the same as the input A. Why? Because no current can flow inside the input of an op-amp. Alright? That means that this point has the same voltage as this point. Hope it is clear. This means that this resistor is like it doesn't even exist over here. So that means that Vx has the same voltage as this point, so it has a voltage of Va. Now I can replace Vx over here, and I can say that Vb is equal to Va. The voltage over here is equal to this point, the voltage of this point over here. It happens because of the ratio of these two resistances. It's not always true in these configurations. Now I can work on the below circuit. Alright, let me erase this. Again, working with the same logic, there is a current flowing from here all the way to here and here. It cannot flow inside the input, so it goes like this. How much is the voltage here on this node N? Well, the voltage here must be equal to the voltage here at this point. How much is the voltage here at this point? Again, no current can flow inside the inputs of an op-amp. That means that this point here must have the same voltage as this point over here. So it must have a voltage of 0. So it is like this, again, is a short circuit. I will use the same logic for here like before, because this current is the same. So we're going to say VA minus Vn over 10 must be equal to Vn minus Vc over 30. Again, for the reasons we explained, Vn must be equal to 0. That means that if you do the math over here, it happens that Vc is minus 3 times Va. We have a minus here. Why? Because this is an inverting op-amp configuration, because the input is on the inverting input of the terminal. In these configurations, the output has a negative sign. When the input is on the positive terminal, the output has a positive sign in relation to the input. Now I'm ready to find Vout. Vout is VB minus VC, alright? Which means that Vout is VA plus 3. Alright, this is VA. VA is nothing but Vin, alright? Vin is VA. Therefore, Vout over Vin must be equal to 4. Alright, that was it for the ideal op-amp. Now onto this case where things are a bit spicier. We have two op-amps with supply terminals of 15 minus 15 volts. And these are saturated at the 14 volt point at the output. We're asked to find again Vout over Vin. Again, I'm going to use the same logic. I'm going to say this point X. For here, alright, we have a common current like before. 0 minus Vx over 10 is equal to Vx minus Vb over 20. The same logic like before, nothing really changed here. And now I'm going to use the equation that I use for all op-amp configurations. Vout is equal to V plus minus V minus times A, the gain. I'm solving in respect to V minus because V minus is my Vx, which I want to replace over here. And I'm going to say that, alright, V minus is Vx, V plus is equal to VA, like I knew before, and therefore I have now a relationship between the output, VA, the input, and the gain, alright, A is the gain, and Vx, this Vx. Now I can replace this over here, and if I do the math, VB turns out to be VA over this, 1 plus 1 over A. Now if I replace the numbers, A is nothing but 15 minus 15, so it's 30. Then I replace it and I have that VB is equal to about 0.97 VA. Close to VA like we had previously, but slightly lower. Now, working on the circuit below, this is a typical inverting op-amp. Now, I can do the same things over here, and I can prove again the V out over V in is C over VA, but it will take too long. I have done this already in a previous video, how to solve the inverting op-amp configuration, if you want to check it out. Otherwise, you can do this as an exercise and tell me how you did on the comments below. Now, for the inverting op-amp configuration, VC over VA, V output over V input, which is going to have this feedback resistor, this input resistor, and the gain. How much is the feedback resistor? 30 kilo ohms. How much is the input resistor? 10 kilo ohms. How much is the gain? 30. I do the math and turns out that VC is equal to minus 2.6 times VA, 6.5. Slightly lower than 3 VA, like we had previously. Now if I erase most of this crap over here, I'm going to find out how much is V out over V in. V out is nothing but VB minus VC is 3.62 VA. VA is V in, therefore V out over V in must be equal to 3.62. Slightly lower than the 4 we had previously, right? Now, op-amp saturates at 14 volts. Saturation means that the op-amp becomes useless practically. The output cannot amplify further than a specific input. So the maximum swing that we are going to find at the output is going to be 14 volts. So VB max must be equal to 40, which means that from this equation over here, I can say that 0.97 of VA max, right, must be equal to 14. Therefore, VA max must be equal to 14.43. Alright, and now a maximum signal that can be found at the input so that this thing can still amplify. How about this lower part of the circuit? Again, VC max is equal to 14. How much is VC max? Is 2.65 VA max, alright, with a minus in front, but it doesn't matter here. Must be equal to 14. Therefore, VA max must be equal to 5.28. I keep this value as a maximum value because it's a smaller value, alright? So this is the smallest value allowed at the input, so that we still have some type of amplification over here. Otherwise, my input signal is going to be distorted, let's say. How much is V in? Well, the peak-to-peak voltage must be 2 times 5.28, 10.56 volts. That means the input signal must be, alright, this is wrong, must be 5.28 sine omega t, whatever is the signal over here, alright? This is the maximum amplitude signal that I can accommodate at this input, so that I have an output over here that is not distorted. Now we're asked to find how much is this value in RMS, alright? How much is the equivalent RMS value? It's very easy. I just say that it's a big peak-to-peak voltage over 2 square root of 2. So it's 10.56 over 2 square root of 2, which is 3.73 volts. And that's it. Check out the op-amp playlist over here for more op-amp videos. Study well and take care. Bye bye.